back to another video. And this video I'm doing from my home because I am at home right now. So in the previous video I had introduced the concept of likelihood functions, but I did not give any examples on how to use them. So in this video I'm going to give some examples on how to use likelihood functions to estimate parameters. Okay, so let's say we have taken n draws from an exponential distribution. So we are given that we have taken n draws, and let's just assume that they are independently and identically distributed from exponential flash, because I'm wearing flash. Okay, now, but the thing is that we don't know what the value of flash is, right? So that is what we're trying to estimate. Now for that, let's say we want to find the maximum likelihood estimate of flash. So what would we do? So now you might recall that the likelihood function of flash given the value of x is basically just the product of all the distribution function of xi's given flash, right? And now we know that the distribution function of this is basically flash e to the power minus flash xi. That is just the the density function of exponential flash, right? Okay, and I am not really sure if I mentioned this in the last video, but if you want to maximize the likelihood function, you could also maximize the log likelihood function, because log is an increasing function. So they both would have the maxima at the same point. So if we look at log likelihood of flash under x, that is basically going to be over this side I equal to 1 to n. The log would basically convert the product into a summation form. So that would make the summation from 1 to n of the log of the density function of xi under flash, right? And this we basically have summation I equal to 1 to n, and that would basically just be log of flash minus flash xi, right? And we need to find the maximum of this. So that would basically just be arg the max. Like arg max basically means what is the value of this parameter at which this function is maximum, the argument arg max. Or I think there's a function in NumPy also called np.argmax. I am not really sure, you could check that out, but that is only for discrete values, because NumPy is arrays. Anyway, so now what we can do to find at which point this function attains maximum is by differentiating with respect to flash. So that would basically give us equal to 1 to n. So that would give us 1 by lambda cap 1 by flash minus xi. The summation is equal to 0. That would basically give us n by flash is equal to summation xi, which would basically give us that the maximum likely estimator of flash, the MLE, is basically equal to 1 by xn bar, or 1 by the sample mean of the values which we have collected. Right, so in cases like exponential distribution, we have a straightforward answer, right? We have a direct answer. You have n variables, you can directly find 1 upon the mean. But like in some cases, like gamma distribution, where we want to estimate alpha and betas, we won't have a direct answer. So I will show you an example of that. Alright, so now let's look at the gamma example. So let's say we have xi's identically and independently distributed from gamma, alpha, comma, flash. Okay, and now we need to find the maximum likely estimators of alpha and flash. So this is our density function for the gamma distribution, which you have right here. And now we'll proceed similarly to the exponential case. We will maximize the log likelihood function which is basically summation of log of f of xi given alpha comma gamma from I equal to 1 to n, right? And that is basically I equal to 1 to n. It's so much easier to work on this than my college board. It's so much bigger. Yes, has so much space. Yeah, so that's minus log of gamma alpha, okay, minus alpha log flash plus alpha minus 1 log xi minus xi by flash. Now, how would we proceed to maximize this with respect to two parameters? So first we would take the partial derivative with respect to flash, then the partial derivative with respect to alpha, set both of them to be equal to 0, and we're done. Okay, so how would we proceed with that? Now, partial derivative with respect to flash is basically summation I equal to 1 to n. This is 0, this is minus alpha by flash plus xi by flash, because this is 0 with respect to flash. Basically give flash cap is equal to xn bar by alpha cap. This is the first equation we have. Now, taking the partial derivative with respect to alpha basically gives us, now the derivative of a log of a gamma function is basically the digamma function. So that is basically minus, I am not really sure how to represent it, I'm just going to call it this, minus digamma of alpha minus log of flash plus log of xi is equal to 0. Now already you can see how complicated this equation is, right? Because this, it's, yeah. Now this again, it can be represented as a log of xn bar minus log of alpha cap. But to simplify it overall, this function does not have a closed form solution. So now we can't find a closed form solution for approximating alpha, for getting the maximum likelihood estimators of alpha and flash. So for that we would implement other tricks like gradient descent or Newton-Raphson's methods, among others. But I think those two are predominant. I think gradient descent is predominantly used. Now there are more algorithms other than these two, but I will probably cover gradient descent and Newton-Raphson's in the next video to show you how to solve for estimates like these. Well, all in all, I hope you enjoyed this video, and please like, share and subscribe to my channel and videos, and share with your friends, comment below it. And yes, I did not have a proper helmet or something, so I made it out of two caps.